this exercise is focused on one of the challenges, one of the last year challenges, which is concerned with providing a data stream of Sentinel-2, which it's no big news, but the new factor is that this data is filtered and gap-filled with the objective of providing a continuous stream of data free of clouds and artifacts. We'll talk a bit more about this in the next few slides. And as to the topic, the agricultural mapping, you may wonder why would the UN agency be concerned with high-resolution agricultural mapping? And the relevance for the World Food Programme is that changes in cropland extent are, a major factor in humanitarian assistance, because in many environments, that's what determines the volumes and quantities of food available to local populations. And in a setting of conflict, and conflict has been a major driver of the WFP's requirements in humanitarian assistance has been conflict. And the image you see in South Sudan compares two situations around a location called Payok in South Sudan from 2016 to 2017, showing through a simple kind of temporal composite of Sentinel-2 data, the abandonment of cropland around this location. So this is one of the kind of major drivers for us to get a grip on the extent of cropland, to do it in a more dynamic way and to assess its year-on-year changes. There's also the advantage that in many settings of countries without organized data collection procedures, in the case of many countries like South Sudan, Central African Republic, there's very little idea of the extent of cropland and its crop makeup. So it's also an opportunity to, in many of these areas, to provide a first-time cropland baseline. The WFP also has a strong line of work in technical assistance to governments, and hence in countries where there is already established procedures of agricultural assessment, there's still the advantages of bringing in new technology to help governments to do a better job out of these in these areas of work. Ourselves, the WFP, we engage in a variety of interventions that are not necessarily just the classic provision of food. We also have work on, for instance, smallholder support systems. And in that case, there could be a case made for cropland information to assess the seasonal performance potential of the areas of intervention, and the likelihood of meeting procurement targets, because the WFP does have as well initiatives on procurement of cereals from smallholder farmers. And you could look at potential changes from staple to cash crops and vice versa in the areas of intervention. And finally, also in terms of the direct interventions like index insurance and the resilience building interventions in different areas. So that's the relevance and motivation. And we do have an operational system that we use for crop type mapping efforts. And this involves, of course, the Sentinel data and Landsat 8 data as well as the primary data set. One of the big strengths of WFP is very deep and wide field presence. So we find it, well, relatively easy. You still have to do the job, but it's far easier for us than it is for maybe other agencies or institutions to carry out extensive campaigns of ground data collection. And we do that using established procedures of using simplified smartphone tools like ODK. And all this data is usually captured in the field, it's immediately uploaded. And we have an agreement, and we use the resources of the Earth Observation Data Center in Vienna, where we installed a software system called Sen2Agri, which was developed by the European Space Agency. And if you get everything right at the end, you get a crop type product, so a classified image showing the different crop types existing in a region with given performance assessed by classification assessment metrics. This is the nature of the field work, and you will be dealing with some of it as the raw material for your exercise. Essentially what we do, we train local teams to capture preferably geo-referenced perimeters of different crops. So people walk around the fields, make annotations on the crop type and development stage and other bits and pieces of information. If you're facing regular fields, large, then you can do tracks along roads, and for huge fields, you may just take a single point inside the field, and then there's some work in the back office to derive the polygons that are required by the Cent2Agri system. This is the kind of stuff that we want to obtain. I mean, this is a zoom in a particular area. This is in the border between the Darfur region of Sudan and the West Barghazal state in South Sudan. There's, fewer more remote areas you can think of, but still we can do a very decent job of mapping the extent of cropland and the kind of makeup of the cropland that you see. Usually we are able to do this at country level. So we did the first countrywide, so country scale crop type mapping for South Sudan with data from 2018, and we hope that will become an operational activity from 2021 onwards. Now this has been working well, the Cent2Agri setup, but at the moment it really only uses Sentinel-2 and Landsat-8, so there's no use made of SAR. There is a module for atmospheric correction, but in places with significant atmospheric interference, this may still impact on the quality of the classification. Now, as part of our work in processing Earth observation data, we developed a flexible data-driven pixel-optimized filter that both gap fills, removes noise, and actually also does temporal interpolation if you want to, which we've been using and applying routinely to medium resolution data, mostly NDVI and land surface temperatures. The objective is to provide us with smooth, clean images without, things like mosaicing artifacts or cloud-inflicted gaps. I'll send you the paper that there's actually a lot of literature on the subject, but the specific filter I will make a link or actually share the PDF of the paper that was published back in 2017 that gives you the mathematical details of the filter. And the question we set ourselves is, can we apply the same filter to Sentinel-2 data? Of course, that would be very good for hazard mapping, where you need Sentinel-2 data, for instance, to map the extent of floods or the extent of problems in agricultural areas. But the question is there a benefit of using the filtered data for crop type or, more generally land cover classification efforts? The picture you see is kind of a, kind of thing you get out of the filter if you look at a time series. So this would be for a specific pixel, and you can see this being applied to a whole raster on a pixel by pixel basis. Of course, the filter is kind of expensive in terms of, and actually, let me just show you, this is the impact of the filter. So this was a brief experiment we did. On the left, the raw data, on the right, the filter data. And the filter data obviously is able to fill the gaps arising from lack of coverage or cloud, and you get a steady stream of data without gaps, artifacts, or cloud interference. So the issue is, beyond providing nicer and prettier pictures, is there some more tangible benefits to the user of this filter? Because the filter is relatively expensive, and we optimize it extensively. So, but still, it's reasonably expensive, and applying it to very large data sets, such as Sentinel-2, it should be justified. In terms of the technical behavior of the filter is quite attractive because it's modulated by two parameters. One that controls the amount of smoothing, and the smaller the numerical value of this parameter, the closer to the original data the resulted filtered output is. And you can see on the top left chart, using a low value for the coefficient gives you an output which is smooth but still follows very much the original shape of the input signal. Whereas if you tune the coefficient upwards, then you get a very smooth curve with much stronger reduction in the amount of noise. And the crucial thing is that this S value can be optimized and is optimized in operational practice to some optimum value that in principle would apply only just the required amount of noise. The other parameter is a so-called p-value that kind of controls the asymmetry of the output. And this is a value between 0 and 1. If p is 0.5, which is what you get in the middle chart of the panel on the left, then it's a kind of classic smoothing in that the filtered output goes, say, through the noise. If you set the p-value towards 1, you get the stuff on the top, which means that the smoother output adjusts to the upper envelope of the input data. And this is what you exactly want for things like NDVI, where the noise is kind of almost all of it on the negative side. Conversely, if you reduce p towards 0, then you get the kind of the fit is to the baseline of the signal. So, and this is the kind of thing you want for reflectances, where noise tends to increase the value of the reflectance through things like cloud cover. You still have to be careful with cloud shadow. So you can't push the p-value very, very low. Drawback that p is not optimized, so it relies on expert judgment, and a fixed value is applied across the board. But its influence is, of course, the influence when it goes from 0.95 to 0.05 is quite noticeable. But within reason, if you use 0.95 or 0.9, it's not going to change a lot in terms of the output. Focusing on the exercise, you have a nice data set of some 8,800 time series of raw Sentinel-2 reflectances, smoothed Sentinel-2 reflectances, and also SAR data. The smoothed reflectances, the S has been optimized with a value between 3 and 4. And the p-value was adopted and set to 0.2 after visual examination of contrasting the time series in the raw data with a slightly higher value for band 8, 11, and 12. The data essentially consists of pixel time series, and the pixels have been selected inside each agronomic data sample. So I mentioned the type of field data we collect. So the original data set consisted of georeferenced polygons containing as much as possible a uniform crop type or mix of crops. The procedure was to select as many points within each polygon as could fit with a 25-meter distance between them. So I mentioned the field data. So the field data is actually very recent. It was collected earlier in the month, in early October 2020, in northeast Nigeria, in Adamawa State. This is an area that is affected by conflict. You probably heard about Boko Haram and their impacts on local populations. And there's an interest in seeing what there's not really a cropland extent baseline even. So there's several interests here in terms of the outputs of the analysis we're doing. So in parallel, we are currently working using our standard setup to provide the first crop type map for the region. And the crop types you get, maize, millet, sorghum, beans, soya, and their mixes. So you will have samples which contain, for instance, beans and groundnut, maize and millet, sorghum and soya. You know, there will be several mixes. And it could be interesting to see whether we can actually distinguish a pure maize crop from a maize and groundnut mix. You will also have fallow samples, so unused cropland in this current season. And I think we did as well include so-called no ID, which is a field which was planted but abandoned. And the presumption is that it might have been abandoned by through the impacts of conflict. So you'll be provided with 7,000 labeled data, and the remaining will remain unlabeled, which you should classify, and that's what you're going to use for an assessment of the quality of the method that you come up with. So that's essentially the exercise. So you need to devise a classifier for crop types to be run with the various data sets and to compare results. You know, we need to give you as much freedom as you like, but you know, in a way, what we would like, and it's a suggestion. I mean, you know, you're supposed to have fun in these things, so you have some latitude and freedom to do as you please. But the kind of thing we would be more interested to see coming out of it would be some initial, you know, we're not going to resolve this problem today, but some comparisons of what you get by using the raw Sentinel-2 versus what you could obtain using the filtered Sentinel-2 with and without SAR. So it's a bit entirely up to you what how you approach the problem, which data sets you're going to use out of these three, so raw Sentinel-2, filtered Sentinel-2, and SAR. And you can use them in different combinations. But we would like to see some contrasts, especially between the raw Sentinel-2 and other combinations. I think you know, in principle, this exercise should be individual, maybe, but you know, if you know each other and you want to team up, I guess it's okay. So we're not setting a lot of rules besides giving you this data and these broad orientations. But in principle, if you set something going, you can produce your predictions for the unlabeled data, and then you can submit them, and then we will see how well you did. And I think that's pretty much what I had to say for the moment. I hope you enjoyed the work, and I thank you for being present here.
I tried a different model, so I tried a different, in fact, with gradient boosting classifier. Mm-hmm. And well, it gets, I would say, comparable predictions. Maybe the let's say the misclassifications are different, but overall I don't think the accuracy is much better or worse. It's more or less comparable.
Okay, yeah. This is normally what I experience as well with this data. Trying different models sometimes doesn't help much as like changing the inputs or changing like important hyperparameters.
But increasing the size of the trees increase a bit let's say, you get better results. But of course, it takes longer than to train the model.